Okay, we are trying to review a little bit about the triple integral, especially set up the triple integral in the cylindrical coordinates. And one thing we want to say is that setting up the triple integral is sort of complicated, especially if you have no idea that what the domain of integration really is. And it'll help to have some sort of realization when you look at this domain in the question, and you can either use any graphic software to plot this domain and get the sense, or you can try to get familiar with those quadratic surfaces essentially and the plane, right? And for us, the most maybe we should talk about the standard procedure. If the domain is not so clearly stated, but rather given by some sort of surfaces in top, bottom, or left, right, those kind of thing. For example, here, um, when we were giving one surface, quadratic surface over there, and then we also were giving this plane. This plane is relatively easy. It is a plane that parallel to the xy plane and at the height of z equals 2, if you look at this, right? But this surface given here is a paraboloid, is not so straightforward, right? But we should have some sense what this surface look like, because you can see the standard form of the paraboloid will be a z equals x squared plus y squared, right? So in that case, we have the paraboloids opening up. But for this one, we can see there is a maximum possible value for the z to take when x and y. So for this, when x and y are both 0, z reach the highest possible value, which is a 14, right? And then you would imagine by adding any value to x and y, which are not 0, you will have a smaller and smaller z. So you would essentially think this paraboloid is opening downwards. All right. And then you would imagine, you would think about when both x and y equal to 0, z, so at x equals 0, y equals 0, z is 14, which is well above this plane z equals 4. Now you would have some sense that what does the shape of the solid really look like. It will be a curved surface paraboloid on top, all right, and the plane is cutting it so that the volume is you are having is indeed having a flat surface. So you would imagine z is bigger than 2 and less or equal to 14 minus 3 times x squared minus 3 times y squared in your volume. All right. And over which point of xy we would have this volume obtained. Well, there's one thing, right? So this plane z equal 2 will essentially intersect with this paraboloid. And if you're able to find the intersection, which will be a curve, and then think about it, you jump on top of this surface, z equals 14 minus 3x squared minus 3y squared, you would be able to look downwards and see the projection of the whole volume on the xy plane. And that intersection, will tell you the contour of this projection. So after you determine this contour on the xy plane, you will be able to tell what are the x and y, um, what is the domain for your x and y to be chosen, so that you nail this lower z and upper z. So this is the idea. You got to figure out what is the intersections. What is the curved intersection? So here for us, intersection is obtained by finding the solution of those two equations. We put those two surfaces together. So we see 2 equals 14 minus 3x squared minus 3y squared. So we get, well, we subtract 2 to both sides. And then we add 3x squared and 3y squared. On both sides, we have 3x squared plus 3y squared equals 14 minus 2, which is 12. And then we can divide 3 to both sides. We get x squared plus y squared equals 12 over 3, which is 4. So now you can see you have the circle. So we have x squared plus y squared equals 2 squared. So the projection of the volume on the xy plane is indeed a circle with a radius 2. All right, and now so we can write down the volume in terms of Cartesian coordinates first. Even the question is asking us to set up the triple integral. So another thing is the volume integral. The volume integral means triple integral in our setup. Okay, so even it asks us to set up in the cylindrical coordinates, we would start look at the volume in the Cartesian coordinates so that we get some sense what it look like. So we know the x and the y has to be chosen from this disk, and with that x and y fixed, we have z to be less than 2 and bigger than 2 and less than 14 minus 3x squared minus 3y squared. Okay, so this 2 seems to be coincide with the z equals 2 there. It is not. So we have to say something about that. Before we do that, let's just convert this E region into the cylindrical coordinates. Okay, so for this disk, we see the theta angle will be from 0 to 2 pi, and the radial distance will be from 0 to 2. And for this z, it will be bigger than 2 at 0 and less than 14 minus 3 times. Here, remember, this is a 3 times x squared plus y squared, which is r squared. Okay, so the triple integral we should set up is for the theta from 0 to 2 pi, r is from 0 to 2, and z is from 2 to 14 minus 3r squared. And then we have r times dz dr d theta. So this r is the actual Jacobian determinant. Okay, so similarly, we can have a similar question asked. So given the surface z equals for example, 10 minus 3x squared minus 3y squared, and z equals 4, for example, find the volume bounded by the two surfaces, the paraboloid and the plane. How do we do that? Well, we're doing this in the similar way, right? So here, we first find the intersections of this surface. Z equals 10 minus 3x squared minus 3y squared, and z equals 4. So this tells us 4 equals 10 minus 3x squared minus 3y squared. So this is indeed 3x squared plus 3y squared equals 6. So x squared plus y squared equals 2. So now this tells us if you jump on top of this surface over here, and you look downwards, and then the whole volume over here is projected on the xy plane within this disk of radius square 2. All right, so the volume obtained will be and then obviously our z variable will be bigger than 4 and smaller than 10 minus 3 times x squared minus 3y squared. All right, remember, now you can see this radius is not the same number of this. And the key for us to figure out the projection is to find the intersection. And now with this, we can also represent this volume in the cylindrical coordinates, which has theta is between 0 and 2 pi, r is between 0 and square root of 2, and z is between 4 and 10 minus 3 times r squared. And the triple integral set up in this second example will be theta between 0 and 2 pi, r between 0 and the square root 2, and z is between 4 and 10 minus 3 r squared. The integration is on 1 times r dz dr d theta. So those are the typical problems you would run into, and the key again, as we said, in identifying the domain of the integration of the solid or volume is to find the intersection and project it onto some plane. And typically it is xy plane because we try to make things easier. But remember that to actually get this volume to be described clearly in both the Cartesian and the cylindrical coordinate, you need to find the contour. You need to find the intersection. Otherwise, you will not know where the volume really is. Okay, so this sort of wrap up the discussion of the triple integral in both cylindrical and spherical coordinates, and we will review a little bit later in the last section for the quiz. But then now we are going to start to discuss a new topic.